All right, we're going to do some practice problems here, talking about acid-base chemistry. So let's just go ahead and get started with case 3. A 40-year-old woman comes in, rheumatoid arthritis. Ooh, RTA, rheumatoid, kidney stones. Ooh, ooh, ooh. Love it, love it, love it. All right. Let's take a look at our pH first. So following the steps that we talked about, number 1, pH, we see that we're in an acidosis. Number 2, we look at the bicarb. We see that we have a bicarb of 16, making this a metabolic acidosis. Our next step for metabolic acidosis specifically is to calculate the anion gap. And here we see the anion gap of, let's see, chloride plus bicarb would give 126, minus sodium would be 14, and normal range is about 14. So we're going to call this a non-anion gap metabolic acidosis. And then to check to see if we have appropriate respiratory compensation, we'll use Winter's formula. Remember, Winter's formula is only looking at a respiratory compensation and nothing more. So we're trying to predict what the CO2 should be. Do 1.5 times bicarb, which is 24 plus 8 equals 32, and we see that we do have appropriate respiratory compensation. Perfect. Then the question would become, why does this patient have this non-anion gap metabolic acidosis? And as I said, history of kidney stones and RA go in line with an RTA. So the next thing that you should do is, number 1, check the urine anion gap by using this formula right here. Usually it's supposed to be negative, but in the RTAs type 1 specifically, it is positive. So next thing you'd want to do is give the patient an acid load. And if the patient's blood is acidic, then what should the urine be? Of course, the urine should also be acidic, but in the case of RTA type 1, patients are incapable of acidifying the urine because they don't reabsorb bicarb in the proximal tubule. So all of the urine that comes out is basic. So that's what you should do secondly if you suspect RTA type 1. All right, case number 4. What do we have here? 75-year-old man, long-standing history of severe COPD, so we're going to suspect at least some chronic respiratory acidosis problems. Let's take a look at our pH following our steps, pH and bicarb, first and second. So with pH, we see that he is in fact in an acidosis. Let's look at our bicarb next. We see the bicarb is elevated. That is not in line with metabolic acidosis. So let's check our CO2. We see that we have an increase in CO2 by about 30. So that would put us in a respiratory acidosis state. So respiratory acidosis. And then let's see here. So conceptually, what's going on is we have an increase in our CO2 from baseline, about 30 points. So we would suspect appropriate compensation to be an increase in bicarb. We do see the increase in bicarb. They're going in the same direction, making a mixed disorder less likely. So the question is, by how much should the bicarb be expected to rise? And again, because this is we're suspecting a chronic respiratory acidosis here, then we're going to use the chronic formula. And remember, I said that when you are adjusting bicarb to compensate for respiratory problems, it's easier for the body to get rid of or decrease the bicarb than it is to generate new bicarb. So in this case, we're trying to generate new bicarb, so it's going to be a little bit less. So therefore, we're going to use the numbers of 1 and 3.5 acute and chronic respectively versus 2 and 4 acute and chronic respectively, that we see in respiratory alkalosis compensation. More on that to come. Anyways, so we will apply our formula again. We know the increase from baseline in carbon dioxide, so we're calculating what our bicarb should be, and this should increase by 3.5 for every 10, right, of increase in PCO2. So for every 10 it'd be 30, because we have an increase of CO2 from baseline of about 30, divided by 10, which would equal 3, and 3.5 times 3 is about equal to 10. And we do in fact see that our bicarb is deviated from baseline of 24 by about 10, confirming this is a chronic respiratory acidosis with appropriate compensation. Next, 50-year-old man is found obtunded and poorly responsive. Arterial blood gas is showing an alkalosis. Let's write that down. And let's look at our bicarb next. It's increased, so we have a metabolic alkalosis. Okay, what do we expect our CO2 to do? Well, this should go in the same direction. We do see that the CO2 is increased as expected, so there's less likely of concomitant conditions going on. So the question is, how much should the CO2 rise? And this lovely equation, for every 10 increase in bicarb, the CO2 should go up by 7. So it's a 0.7 to 1 ratio, or a 7 to 10 ratio. So we see that, again, we're in a metabolic alkalosis. By definition, bicarb is increased. How much is it increased? By 10. How much CO2 should increase for every 10 in bicarb? And the answer is 7. So we do see that the PCO2 is increased by 7, while the bicarb is increased by 10, making this a metabolic alkalosis. All right. Oh, and this is a continuation of that case. Sorry about that. So the question also becomes, what is the cause of this man's metabolic alkalosis? And there is a short list. So most commonly, you're going to have dehydration and contraction alkalosis. So you're going to want to check the volume status of the patient. That's the first thing that you should do, right? Because if a patient is dehydrated, they have dry mucous membranes, they have skin turgor, all of that. Let's say they've been vomiting, they're on diuretics, what have you. They are likely in a contraction alkalosis. Important to note that this condition does correct with saline or with implementation of chloride. Same with diuretics, vomiting, etc. The only thing that does not correct with chloride or saline is going to be hyperaldosteronism, also known as Conn syndrome. All right, so let's go to case 7 here. A 50-year-old man with diabetes comes into the emergency room with confusion. I suspect DKA. His wife says he's been thirsty, he's been urinating frequently, and taking narcotics. Narcotics can slow respiratory rate. I wonder if there's a concomitant respiratory acidosis going on along with the suspected DKA. Let's investigate more. He's been taking more pills. All right, let's look at our pH first. Step 1, we do see we're in an acidosis here. Next thing we do is look at bicarb. We see a bicarb is decreased, so we know that we have a metabolic acidosis. Next step in metabolic acidosis only is calculating an ion gap. Let's go ahead and do that now. We see we have a bicarb of 12, a chloride of 94, so 94 plus 12 is 106. So we have 134 minus 106, which I believe is going to be about 28. So we know that we have an anion gap metabolic acidosis. Okay. Next thing we want to know is if there are Well, there's two things we want to know. Number one, do we have appropriate respiratory compensation? And number two, do we have either an additional non-anion gap metabolic acidosis or metabolic alkalosis going on concurrently? So to do that, we're going to use the delta-delta formula. The delta-delta formula as review, all it's stating is the difference from normal from the anion gap. So we see that we have our anion gap is 28, so normal is about 12. So the variation from normal is 16. And then we check our bicarb, and we see our bicarb is normal is 24. Our variation from normal is about 12. And so we see that these numbers are very close, and so we do not suspect that there is an additional disorder going on metabolically. But if we wanted to actually do the delta-delta, we would put these numbers, so 16 over 12, and I think we get like 1.3 or something. So again, 1 to 2 is normal, so this is normal range of a delta-delta. Okay. So next thing we would want to do is check to see if we have appropriate respiratory compensation. So again, by definition, metabolic acidosis, we have a reduction in our bicarb, so we want to know what the change in CO2 should be. So we'll do 1.5 times 12, which would give us 18 plus 8, which would be 26 plus or minus 2. And all right, so our PCO2, our actual PCO2 is 40, which is more than expected. So if we have an increase from expected CO2, then we would suspect a respiratory acidosis going on as well. And that, again, makes sense. We suspect that this patient came in with DKA as well as decreased rates of breathing from his narcotics, giving us a respiratory acidosis. Okay, case number 8. 6-year-old woman presents to the ER, massive vomiting for 3 days. Again, vomiting, dehydration, suspect metabolic alkalosis. On exam, hypotensive, tachycardia. What can also happen when a patient is severely hypotensive is tissue can start dying, and tissue that's dying or not getting enough oxygen, rather, will switch to anabolic metabolism, and the byproduct of anabolic metabolism is lactate. So hypoperfusion and lactate go together. Shock, sepsis, lactate, they all go together. So now we're switching our mindset from metabolic alkalosis to potentially an anion gap metabolic acidosis. But just back that before we even look at our pH here. So in fact, we follow the steps. Step 1 is look at the pH. We do see we're in an acidosis here. Step 2, look at the bicarb. So we see we have a decrease in bicarb, so we have a metabolic acidosis. Step 3 for metabolic acidosis only, calculating the anion gap. We see we have a bicarb of 10, we have a chloride of 79. Wow. Okay, so we have 140 minus 89, which would give us 51, an A gap of 51. Wow. Okay. And we did confirm that we do have an anion gap metabolic acidosis with a gap of 51. That is huge. Next thing we would want to do is see if there's another disorder, metabolic disorder going on. We would use the delta-delta for that. So we see that our change from normal in our anion gap is 39, which is, again, huge. And then we see our variation from normal with our bicarb to be 14. And when we apply our formula, we see that this is greater than 2, letting us know we have a metabolic alkalosis going on as well, again, just as we suspected. But to put this conceptually, without having to apply a formula and just memorizing that greater than 2 is a concomitant metabolic alkalosis in addition to the anion gap metabolic acidosis. Conceptually, you have to understand that, again, the amount of bicarb present should be reduced, rather, by the same amount that the anion went up, the acid went up. So what this is saying is that there's a 39 value deviation from normal. So in other words, there's an addition of 39 components of acid hanging around. What the body should do in that case is drop 39 units of bicarb from normal. So from normal, it would be what, a -9, but obviously that's a negative number is not feasible in medicine. So already by having a positive number, we can see that this patient has an increased bicarb from what is expected. Again, what's expected is 24 minus 39, which I don't even know if I did the math right on that. Did I do the math right on that? Or that's 15, excuse me, 15. It's supposed to be -15. So, again, we see that the bicarb is 10, which is greater than -15. So what metabolic conditions account for a greater increase in bicarb than what should be? And the greater increase in bicarb is alkalosis, metabolic alkalosis. That's how we know. Okay, that's 2 ways to figure out the same thing. And then just for completeness sake, we will calculate the expected change in PCO2. Again, let's just go back to the basics. We know that we have, by definition, a metabolic acidosis by the reduction in bicarb. We would expect the same direction reduction and compensation, so the PCO2 should go down. We see it did go down from 40 to 24. So let's apply our formula here. CO2 is bicarb times 1.5, which will give us 15 plus 8 plus or minus 2, which would be 23 plus or minus 2, and we see we have a PCO2 of 24. So no concurrent respiratory conditions going on, but we do have a anion gap metabolic acidosis and concomitant metabolic alkalosis going on, and again, fits with the patient's history, but follow the steps and you will get to the right answer. Thank you.